In the early 2000s, the world of computing underwent a massive shift. We moved from 32-bit architectures to 64-bit. This wasn't just a number change. It expanded our addressable memory from a measly 4 gigabytes to a theoretical 16 exabytes. But this transition came with a hidden cost that most developers ignore today. We call it the pointer tax. While your logic stayed the same, the metadata required to manage your objects suddenly doubled in size. If you are building high-scale systems, this isn't just a technical detail. It is the difference between fitting your working set in a single server's RAM or paying for an expensive distributed cluster. Let's look at why your objects are taking up more space than you think.
To understand the tax, we have to look at pointer itself. A pointer is simply a memory address, a street number for data. In a 32-bit system, that address is 4 bytes long. In a 64-bit system, it is 8 bytes. This sounds trivial. It is only 4 extra bytes. However, modern software is essentially a massive graph of objects connected by pointers. Every time you use a reference in Java, a pointer in C++, or an object in Python, you are paying this 8-byte fee. In data structures like linked lists or trees, the pointers can actually outweigh the data they are pointing to. You aren't just storing your data, you are paying a massive overhead just to remember where it is.
Let's visualize a simple linked list node holding a single 32-bit integer. In a 32-bit world, the node contains 4 bytes for the integer and 4 bytes for the next pointer. Total, 8 bytes. Now look at 64-bit. The integer is still 4 bytes, but the pointer is now 8. But it gets worse. Due to memory alignment rules, the CPU prefers data to start at multiples of 8. So the compiler adds 4 bytes of padding to keep things aligned. Suddenly, that 8-byte node has ballooned to 16 bytes. You are now using twice as much memory to store the exact same information. This is why a simple collection of millions of small objects can easily consume gigabytes of RAM. When you scale this to millions of objects, the numbers get alarming. If your application manages a cache of 100 million objects, the transition from 32-bit to 64-bit alone could cost you an extra 800 megabytes just for the references. This isn't just about RAM costs. Larger objects mean fewer of them fit in your CPU's L1 and L2 caches. This leads to more cache misses, more trips to main memory, and a significant drop in overall performance. You are paying for the RAM, and you are paying for the latency.
Engineers realized this tax was too high, so they created a clever workaround. In environments like the Java Virtual Machine, this is called compressed OPs, or ordinary object pointers. Since most applications don't actually need 32 gigabytes of RAM, the JVM uses a trick. It stores pointers as 32-bit offsets rather than full 64-bit absolute addresses. When the CPU needs to access the memory, it performs a quick bit shift to reconstruct the full address. This gives you the memory efficiency of a 32-bit system while still allowing you to access up to 32 gigabytes of heap. It is a rare free lunch in computer science, but it only works if your heap stays below that 32 gigabyte threshold.
If you are not in a managed environment with compressed pointers, you have to design for density. The best way to avoid the pointer tax is to use fewer pointers. Instead of an array of objects, use a struct of arrays or a flat buffer. By storing data contiguously in memory, you eliminate the need for pointers between elements and drastically reduce podding. This is why high-performance game engines and databases often use manual memory layouts. They aren't just being difficult, they are fighting to keep their data dense enough to fit in the cache. Remember, the most efficient pointer is the one that doesn't exist.